Welcome to the main lecture for week 11. Here we will cover the expectation variance and covariance matrix. We start with the expectation and variance and standard deviation. Yeah, we saw the lab for this chapter in this address, so you can practice in there with the code that I supplied. Okay, the expected value or expectation of a random variable is an average value for stochastic event, which is the sum of the product of a value obtained by each event and each event's probability. The variance of a random variable is the average of the squared deviation of the random variable from its mean, okay, which is the expected value. Okay, and this variance indicate how far a set of numbers are spread out from their average value. Next, the standard deviation of a random variable, sample or statistical population, data set, or probability distribution is the square root of its variance, like this. The expectation is a product of xi and f of xi, and add all of them, which can be written as e of x or mu. Variance is a the summation of xi minus expectation mu square times x of xi, which is same as e of x square minus mu square. This is written as v of x or sigma square. Standard deviation is just the square root of variance. Okay, just the square root of variance. So it's a sigma or s of x. Okay, with those definitions, find the expected value, variance, and standard deviation of the random variable x, whose probability is like this. Okay, so all you have to do is using, since we have a formula, we can set up the formula. The expectation is the sum of the xi times probability of xi, and variance is the square of variance of xi minus e of x times the probability of xi. And standard deviation is the square root of variance. So with this code, yeah, we can we have variables 0, 1, 2, 3, 4, and its probabilities are given like this. So we listed it. Then, if you just learn it, then you will have expectation mu and variance v of x or sigma square, and the standard deviation sigma, like this. We can do the same thing with the R code for statistics, which you can practice in here without changing the options. Here, just this is the way. Define x and define the probabilities and expectations and variance and the standard deviations are defined in this way. Then you will have the answers like this: sigma, mu and sigma square and sigma, which is the same answers like what you had with the Sage code. Okay, so you can, when you have a different random variable and its probability distribution, still you can use the same code to have the answer for your data. The expectation and variance, the standard deviation of a continuous random variable x can be found as follows. since it's a continuous function, instead of summation, we are using the integral. So expectation mu is the integral from minus 1 infinity to infinity x times of times f of x times dx, and sigma square variance is the integral from minus infinity to infinity the x minus mu square times f of x dx, which is e of x square minus mu square. And standard deviation sigma is just the square root of the variance. So same. It has the following properties. E of x plus b is e of x plus b, and e of ax is a times e of x. And if you combine these two, then it can be written in one form like this. And v of x plus b is equal to v of x. V disappears for the variance, and v of x is equal to a square vx, because we had a square here. And these two equations can be summarized as one in here for the variance. Next, we define g. Let g is equal to x minus mu over sigma. Then this g is called the standard random variable. X was a random variable, and this g from x is a standard random variable. For the expected value of g is 0, and the variance of g is equal to 1. It's very much simplified according to the properties of expected value and variance that we defined. Example 2 tells us to find the variance of x and y when the probability density function f of x is equal to 3x squared and y is equal to 4x plus 2. So this is a continuous function, so expected value mu is from 0 to integral from 0 to 1 and 3x squared dx, which is 3 over 4, and e of x squared is here integral from 0 to 1 and 3x to the fourth dx, which is 3 over 5. And then v of x, which is a sigma square, is equal to e of x square minus mu square. So we have a mu here, and we have e of x square here, 3 over 5, which gives us the variance 3 over 80. And e of y is can be written as e of 4x plus 2, because y is equal to 4x plus 2. So from the property of expectation, so this can be written as 4 times e of x plus 2. E of x was 3 over 4, so the value of expected value of y is equal to 5. And v of y is same as v of 4x plus 2, which is v of 4x here, and which is same as 4 squared times v of x. V of x was 3 over 80, so 16 times 3 over 80 is 3 over 5. So we can find all 4 of the answers that was asked. And this computation can be done simply with the code like this. For the expectation, we had the integration of f t times f of t, and e of x squared is the integral from 0 to 1 and t squared times f of t. So after we define it, if we print it, these values, then this gives us the variance of x and the variance of y. Like this. Okay. I think that's it. Here is the homework problem. Find an example of a continuous random variable x of your interest. Then find the expected value, variance, and standard deviation of that random variable x. Okay, that's it. Second section, joint probability distribution. In this section, we will consider two or more random variables and develop tools to study joint distributions of random variables. We will first discuss joint distribution of the discrete random variables and then extend the result to continuous random variables. The joint probability distribution shows a probability distribution for two or more random variables. The whole point of the joint distribution is to look for a relationship between two variables. Okay? When we know the probability distribution of two random variables together and the probability of one random variable, then we can figure out the probability of the other random variable. Okay, in order to do so, we now introduce a definition of joint probability distribution. Okay. When we have two discrete random variables x and y, the joint probability distribution for x and y is defined as below. P sub ij, the joint probability function, okay, which is written as p of xi and yi, which is same as p of x is equal to xi and y is equal to yi. Okay, the probability when capital X is equal to xi and capital Y is equal to little y of j. Okay, Pij. So we can list all possible p sub ij's in a table like this: p11, p12, and p21, ps1, like this. Okay, we can fill out this joint probability functions here. Okay, we call this p sub ij is the joint probability distribution. Okay. Okay. We call the sum of these in row. We write it as p of x is equal to x1, and this is called the marginal probability distribution when capital X is equal to little x1. And the sum of the second row can be written as probability of when capital X is equal to little x2, okay, and etc. And similarly, the row sum, the sum of all those p1, 1, 1, 2, p21, ps1 can be written as capital P of capital Y is equal to y1. This is also the marginal probability distribution for y when capital Y is equal to y1. Okay. So we call all these and these are called the marginal probability distribution. For x here and for y here. Okay, the joint probability distribution for x and y isn't given. When it was given, the marginal probability distribution is defined as follows: P of capital X is equal to little xi, which is the sum of the P sub ij from j is equal to 1 to t, and P of x capital Y is equal to little yj is the sum of the Pij from I is equal to 1 to s. These are the marginal probability distribution. Here are the properties of the joint probability distribution. For all xi and yj, then p of xi, yj are all bigger than or equal to 0. Okay. All the marginal, all joint probability functions are non-negative. That's what it means. And the sum of Pij is equal to 1. probability sum is equal to 1. And for all ij, when p is in p of x is in interval ab and y is in the interval cd, then this is a sum of all of them. Okay. In between x is in this interval ab and y is in the interval cd. Okay. Okay. These properties can be used for the next example. Suppose there are 3 blue balls and 2 red balls and 3 green balls of the same size in a pocket. And we are going to take out 2 balls randomly. Okay. Let's say that among the balls we took out, the number of blue balls is x, and the number of the red balls is y. So please answer the following questions. Find the joint probability function of x and y. Second, make a table of joint probability distribution of x and y. And find the probability when x plus y is less than or equal to 1. And then the fourth problem is to ask, find the marginal distribution of x. And last problem asks us to find the marginal distribution of y. Okay. Here, we can get the table by using the definition of joint distribution and marginal distribution. As you see, the probability Pij, P sub ij, is the we choose x from 3 blue balls and choose y number of red balls from 2 red balls, and then choose 2 minus x minus y green balls from 3 green balls, over, then multiply all of them, over the choose 2 out of 8. This is the probability of choosing xi and yj. Okay? So with this, we can find p of capital X is equal to 0 and y is equal to 0. Okay? Then what it means is we choose 0 blue balls and 0 red balls and choose 2 green balls only from 3 green balls. So 3 choose 2, which is 3, is the numerator, and a choose 2 is the denominator. So 3 over 28 is the answer for this, and p of x is equal to 0 and y is equal to 1, which means here x is 0 and y is equal to 1, and then we have to choose 1 from the green one. So 3 choose 0 and 2 choose 1 and 3 choose 1 over a choose 2, which is 3 over 14 is this, and p of x is equal to 1, y is equal to 0, then here x is 1, y is equal to 0, then here it should be 1 there. So this gives us 9 over 28, etc. So we can, with this probability formula, that we can find all 9 of them as this. So P11, P12, P13, P21, P31, etc. And lowest sum of this is 5 over 14, lowest sum of this is 15 over 28, and lowest sum of this gives us 3 over 28. Sum of all these is equal to 1. And similarly, we can find the marginal probability distributions. Okay, then we have a table now, and this gives us this gives us the answer. We have the table, and we find all the joint probability functions. And now we are looking for the probability when x plus y is less than or equal to 1. What this means is less than or equal to 1 means 0, 0, 1, 0, and 0, 1, like this. Okay. Then sum of this is the P of 0, 0, P of 1, 0, and P of 1, 1 is this. So sum of these three numbers, which is 9 over 14, is the answer. Next, we are looking for the marginal distribution of x. These are the marginal distribution of x. And these are the marginal distribution of y. Okay. That's what we found. And the last is the, and that's it. I think that's it. So this is the marginal distribution of x, and this is the marginal distribution of y's. Okay, that's it. Next, for a continuous random variable, we use the joint density function. The joint density function f of x, y of a continuous random variable x and y is defined as this. F of x, y is bigger than or equal to 0, okay, non-negative function. Okay. And the integral, double integral of x or over x and y from minus infinity to infinity of, for f of x, y is equal to 1. So total probability should be 1. And the probability of x, when x and y is in this intervals, all we have to do is to do the integration from the interval for x from a to b, from c to d on y. Okay, then this will give us the probability. And the probability of x, y belongs to the area A. Then all we have to do is just find the double integral over that area A. And marginal probability density function of x can be found, the f of x over x, which is the integrate this with respect to y. Then you will give the marginal probability density function of x. And if we integrate f of x, y with respect to x from negative infinity to infinity, then this gives us the marginal probability density function of y. The next example is to find the joint, to find the marginal density function of x and y when the joint density function is given as this in this interval. Okay, then from the above formula, the marginal distribution density function f of x over x is the integral of x plus y from 0 to 1, which is this, gives us x plus 1 over 2. And the marginal density function of y is the integral of x plus y with respect to x from 0 to 1, which is y plus 1/2. Okay. Since we set up the equation, we just define the function and do the integral of f with respect to y from 0 to 1 gives us the marginal distribution of x, and this similar code gives the marginal distribution of y, which is x plus 1/2 and y plus 1/2. It's the same as what we did. You can use the same code for any different joint probability, joint density function. Okay, so when you have a different problem, all you have to do is change the function and the intervals. Okay. Next, covariance and correlation coefficients. It has a star on here, so it's an optional section. So for the beginners, you can just skip it. But I will briefly introduce about the covariance, because we will do define the covariance matrix. Okay. Yeah, we have learned the mean and variance before. Okay. Okay. First, we can think of the mean of x and the mean of y, the expected value. Next, we can use the you can use the variance to see how each variable is spread out. However, the concept of covariance is necessary to understand the correlation between two random variables. Okay, this is the reason that we learn the concept of covariance. Covariance is defined in this way. Covariance of x and y is written as sigma of xy, which is the expectation of x minus mu x times y minus mu y, which can be written as e of xy minus mu x mu y. Okay, this is the definition. Okay. This covariance is the average of the product of the deviation of x and the deviation of y. Okay. Okay. However, there is a problem that the covariance is affected by the size of the unit of x and y. To compensate this effect, we use the correlation coefficient. The correlation coefficient is a statistical measure of the strength of the relationship between the relative movement of two variables, which is defined in this way. Correlation coefficient, rho, is defined as the covariance of x and y over s of x and s of y. So it can be written as this. This is the definition of it. With those the definition, we can define the covariance matrix from the given data. Okay, the covariance matrix for xi xp of p random variables, the p is defined by using a matrix with the covariance between the i's and j's random variables when I is not equal to j. Okay, here the off diagonal entries are covariance. Okay, covariance here sigma 1 2 sigma 1 p, sigma 2 1 sigma p1, and the main diagonal entries are variance of each variables x1, x2, and xp. Okay, so we can if we have a p random variables, then we can find the correlations and the variance to form the matrix sigma, which is called the covariance matrix of p random variables. This is a p by p matrix. Okay. With a simple code, you can find these covariances and the variances as well to fill out these entries. Okay. This matrix is symmetric and positive semi-definite, which means the eigenvalues are all real and non-negative of this matrix. Okay, the covariance matrix can be seen as representing the distribution of data as shown in this figure. Okay, here if it's 1 1, then it's a circle with a kind of normal surface. If we have off diagonal with the minus signs on here, then it's kind of rotated counterclockwise. If it is if the covariance matrix has the positive off diagonal entries like this, then it's been rotated in clockwise directions. Okay, about 45 degrees. If the off diagonal entry is bigger than the earlier one, then the height is a little bigger in this, like this. Okay? So this shows how the distribution of the data looks like. Okay, here is the problem. Given the sample data is follow, find the covariance matrix of these data. We have a data, we want to find the covariance matrix. Here, this can be considered as random variables. Okay, then from this given data, we can form a matrix from this given data. From here, we can find the covariance and variance with this code and form a covariance matrix. Okay, then this gives us the covariance matrix like this. So you can use the same code for any given data like this to find the covariance matrix. Okay, then here is the R code to find the covariance matrix. This will give us the same covariance matrix from the same data. This is the R code to form a covariance matrix. Okay, I think that's the end of the week 11. Okay. The covariance matrix plays an important role in dimension reduction. Okay. And the typical technique of dimension reduction is a principal component analysis, which we will learn in the next week. And the singularity composition is used to do this principal component analysis. Okay, yeah, I explained that we have 3 homework problems in this chapter. I think that's it. Thank you for your attention. We will have a review of what we have done in this lecture. Thank you for your attention.